Okay, I now call on Nick Kusznir, our Lyell medallist, Understanding the Ocean-Continent Transition, Geology and Geophysics in Deep Water. Over to you, Nick.
Thank you. So, yes. Right, I want to use the pointer, so I can still read it from here. Rifted continental margins, as I'm sure you all know, they're formed as a consequence of continental breakup and the initiation of seafloor spreading. Before we go further, though, why are they important? Why do we need to study and know about these things? Well, they're important foremost, I think, because they're a fundamental component of global tectonics and geodynamics. Okay, they're formed by some very important processes, and to understand those very important processes, we need to understand how rifted margins form. But as well, they're important because they host natural resources, mainly oil and gas. They're important for territorial claims, law of the sea, UNCLOS. And they help us to produce better plate kinematic restorations, which can be very important for understanding paleoceanography. Now, in working on rifted continental margins, there are several key questions. What is the ocean-continent transition structure? Where is it? Where is the continent-ocean boundary? And can we globally map these? What we see here is the classical view of rifted margin formation and structure. And I should say, it's largely wrong, okay. The ocean-continent transition, which we see in this wrong diagram here, is obviously located in very deep water, is often usually covered with very thick sediments, many kilometers, sometimes even more than 10 kilometers of sediments. And that makes it very difficult, okay, to see with remote sensing, with geophysics, what is going on in this region. It's also very expensive to drill as well. Now, the last four decades have been exciting. There's been a lot of intense international multidisciplinary research thrown at trying to understand rifted margins, their ocean-continent transition structure, and their formation processes. And this work has been reasonably successful. I'm almost sure we haven't answered all the questions, but we know a lot more now than we did 4 decades ago. And one thing we've learned, first, is that simple, okay, formation model is incorrect. And what we've learned is the structure, and therefore the formation processes, are somewhat more complex than we originally thought. What we see here is the example of a magma pore margin where what we see is, in this particular example, the unroofing and exposure of mantle at the seafloor, which becomes serpentinized. Now, how have we investigated deep water ocean-continent transition structure? Well, the evidence comes from seismology, reflection and refraction, ocean drilling, gravity anomaly inversion, substance analysis, and by looking at the exhumed alpine Tethyan margin, where you can actually walk on this exhumed within the Alps, so fieldwork. Rifted margins, we now know, show a very diverse structure and composition. At one extreme, we've got magma pore rifted margins, where we have suppressed decompression melting. We get exhumed mantle between thin continental and oceanic crust. At the other extreme, we have magma-rich margins where we have excess decompression melting. We get volcanic seaward dipping reflectors, extrusives, magmatic underplate, and usually we start the seafloor spreading with a very thick oceanic crust. If we look in a bit more detail at one of those end members, the magma pore rifted margin example, what we see, and this is the sort of the data we work with from the seismology starting point, reflection seismic data, what we see generically, okay, for the ocean continent transition structure of a magma pore rifted margins is near the beach in the proximal domain, relatively unstretched, unthinned continental crust, obviously some extensional faulting. But as we go further out, we get what we call the necking domain, where we then go into a region of hyper-thinned, hyper-extended crust, where the crust may be anywhere between 15 and perhaps 5 kilometers thick. That's the continental crust. Then, further out, at a magma pore margin, we will see perhaps 100 kilometers, perhaps more, perhaps less, of exhumed mantle, which is serpentinized, and then eventually we start the proper oceanic crust. We see another example here of a magma pore margin. We see between oceanic crust here and the continental crust, either thin or absent crust of any form. This is on the eastern Grand Banks here. But here we see, again, based on refraction seismology, a magma-rich margin from the ISIM experiment. And we see it's very, very different. We see a very large thickness of extrusive SDRs, underplate, and very thick initial oceanic crust. So if we're working on rifted margins, whether for academia or whether for industry, there are several questions we need to know the answer of. One is we need to know the distribution of continental and oceanic crust. Where does the continental crust stop? Okay, where does the oceanic crust start? And have we got something else in between, exhumed mantle? So we need to know the structure of the ocean-continent transition and the location of the most distal part of the continent-ocean boundary. And as well, it's important that we know the crustal type right the way across and its composition. And are we looking at a magma pore, normal, or magma-rich margin? Our approach that we've developed to better understand or interrogate OCT structure and COB location at rifted margins, our approach is to determine these by applying a set of quantitative analytical techniques which we can then bring together. We use gravity inversion to determine MOHO depth, crustal basement thickness, and continental lithosphere thinning. We use residual depth anomaly analysis, sediment-corrected residual depth anomaly analysis to investigate ocean-continent transition bathymetry anomalies with respect to expected oceanic bathymetries. And as well, we can carry out subsidence analysis to determine the distribution of continental lithosphere thinning. As well, if the deep long offset seismic reflection data is good enough, we can carry out a gravity and seismic joint inversion to determine the lateral variation of basement density and seismic velocity. Now going back, okay, to that example we saw a couple of slides back, this is from deep water Angola, the Kwanza segment there. This is the starting point, the deep seismic that we start with. Using those techniques, gravity inversion, RDA analysis, substance analysis, and joint inversion, together we can make an interpretation, or we might start with an interpretation of the seismic. We can use these to validate that interpretation. And what we see here is proximal continental crust. I can't read that, but I think it probably says hyper-thinned continental crust. We do a proper oceanic crust here, and here we've got a transition zone where we've got some very thin continental material with magmatic addition. Recently, as you probably know, the northern margin of the South China Sea has been drilled by IODP. What is the ocean-continent transition structure of this region? Where is the continent-ocean boundary? Well, first, we're blessed with very good deep long offset seismic reflection data, Chinese data. Applying, in this case, the joint inversion of the gravity and the seismic reflection data, we can actually map out crustal basement thickness variation and moho depth, so we get a feel for the geometry of the ocean-continent transition. But we also, from the joint inversion, get the lateral variation in basement density. That's the density between moho and the base of the sediments. And what we see is in this southern distal region here, the basement density climbs up. There's a discontinuity. It goes upwards. And we would interpret that as oceanic crust. Unfortunately, IODP has drilled block ridge A, B, and C, and confirms that ridge B and C are in fact oceanic, while ridge A is hyperthinned continental crust. Where are we? Now, so far we've just been looking at profiles, okay, but can we actually, is there any way we can actually globally map OCT structure and continent-ocean boundary location? Well, that's another thing we've worked on, and we've developed techniques for doing this. We use global mapping of crustal thickness using satellite gravity inversion. I won't say too much about the technique, but why can we do this today when perhaps we couldn't do it 15 or 10 years ago? Well, first is the quality and availability of satellite-derived gravity anomaly data, which is very, very good, particularly over the oceans. It uses radar altimetry, okay, to get a very good satellite-derived gravity anomaly field at the longer wavelengths, 50 kilometers or more that we need. The important bits, okay, of the technique are listed here. Okay, the other important ingredient is that we realize we need to include a lithosphere thermal gravity anomaly correction because the hot lithosphere of the continental margin or the ocean lithosphere against the margin is hot, thermally expanded, and generates a very large negative gravity anomaly, which we need to include within the 3D gravity inversion. We use a 3D spectral technique to do the inversion, and we invoke a thing called Smith's theorem, which for the assumptions we make gives us a unique solution. So we're not using moving polygons around, it's more like processing seismic data. The technique has been described in its gory mathematical geophysical detail in many papers. But here we see a map of global thickness, global crustal thickness for the Indian Ocean. The blue here are crustal thicknesses, probably 8 or so kilometers and less. And as you can see, we can pick out quite well the blue areas of oceanic lithosphere. The reds are probably 25 to 30 or more, and these will correspond generally to continental crust. We've got some orange stuff within the oceans, okay, Kerguelen, Chagos, and sort of Madagascar Ridge, for instance. These correspond to intra-oceanic plateaus, not necessarily with any continental material in them. But we can spin around the world. There's the Western Pacific. There's the Eastern Pacific. The Pacific is huge, okay, as we can see from just going around 90 degrees at a time. And here's the Atlantic. But we can zoom in and look in quite substantial detail at the nature and geometry of margins and their conjugacy across the ocean. Where are we? Now, the gravity inversion technique produces 3D data volumes of moho depth and crustal basement thickness, and we can arbitrarily cut out cross-sections anywhere and build cross-sections from those 3D moho depth grids. So here we see a set produced for the western margins of Africa, of West Africa. And if we look at one of these, I think it's this one here in a little bit detail across the Guinea High, we can actually get this sort of amount of detail basically from this global analysis. Many years ago, perhaps I think 11, 12 years ago, we produced the first maps for the Arctic. We can see where the ocean basins are, the Canada Basin, the Eurasia Basin, these little basins, Podvodnikov and Makarov. This is a more recent improvement of that mapping. Again, we can cut out cross sections, and if we do this, okay, the base of the brown here is the Moho from the gravity inversion. So this is running from the East Siberian margin across the Podvodnikov and Makarov. So we can see OCT structure here. Whether this is thick oceanic crust or thin continental crust or a mixture, we don't know. But in red, we've got an independent measurement from Russian refraction experiments, okay, which suggests the gravity inversion mapping isn't far wrong. We've also looked, working with British Antarctic Survey, at the Southern Oceans and Antarctica, but that's very much work in progress. Now, to finish off, one of the applications of this global mapping of crustal thickness and OCT structure and location is within plate reconstructions. We can use the global crustal thickness mapping to test, improve, and better illustrate plate reconstructions. And what we do is take our global grids of crustal thickness, take them into the plate reconstructions. So for this purpose, we're using Dietmar-Muller's G-plates. Let's look at the Indian Ocean. Okay, this is the present day crustal thickness. If we restore to 84 million years, we can see that Madagascar here is snugly huddling up to the west coast of India. Let's just take this a little bit further. 68 million years, we formed the Mascarene Basin. We're forming a thing called the Gop Rift here, but Seychelles is still really attached or close to India. Take it a bit further, at 56, Seychelles has moved off India, and seafloor spreading is propagating southwards. As we take it further, okay, to 48 million years, we stopped seafloor spreading. We've stopped earlier seafloor spreading in the Mascarene Basin, and we get a rather complex set of strike-slip faults, and a battle, really, between crustal accretion here, I think, between Nazareth and Mascarene Banks and Chagos, as magmatic addition is trying to create crust, or is creating crust, and rifting and extension is trying to pull it apart. But eventually, at 40 million years, we start to, the seafloor spreading here starts to break through to that going on down here, and by the time we get to 30 million years, we've got the first oceanic crust coming through here as Chagos is pulled out of the Mascarene Banks. And this is the present day picture with the black dots showing the present day earthquake activity. So thank you for listening. I'll leave you with this illustration of the separation trajectory of Chagos Banks, okay, from the Mascarene and Nazareth Bank here. Thank you very much.
Thank you very much, Nick. And before we break for a slightly earlier than scheduled coffee break, does anybody have any questions? Right at the back, if the microphone can...
Brian Lovell, University of Cambridge. Nick, thank you very much. Over 20 years ago, you published what many of us found a very helpful paper describing transient uplift on a magma-rich continental margin. That was the North Sea, 55 million years. As I recall, it was a pretty hefty transient movement of the order of 700 meters.
750, yes.
Yeah, okay.
Yeah.
Can you give us a word on the possible interaction between what we assume are time-dependent changes in mantle convection and the geological settings you've described to us today?
I think well, within the Indian Ocean especially, the evolution of the Indian Ocean appears to have been marked by many ridge jumps. Now, the question is, are they related to global plate reorganizations, which could force that jump, or are they due to hot spots or wet spots, okay, attracting, well, a rheological issue, okay, moving the plate boundary to a weaker place. And when we look at features like this, but further down, we've got Kerguelen, we've also got Conrad Banks, we've got Crozet as well. I don't believe that thick crust is continental. I think it's magmatic, and almost certainly that would have been associated. Well, the question is it associated with a hot spot or a wet spot? Now, what the vertical motions, what the mantle dynamic tomography was, transient associated with those, I don't know. But certainly the sort of thing you've referred to in the North Atlantic, I think is being very pervasive in the Indian Ocean.
Thank you. And another question in the middle from Rob.
Rob Larson, British Antarctic Survey.
There's a microphone coming.
Sorry. Rob Larson, British Antarctic Survey. So presumably in your inversion procedure, where you're trying to get crustal thickness, presumably bathymetry is one of the inputs.
Yes.
So, and in many cases, because we've only got something like 10 or 12% of the oceans covered with real bathymetry, the bathymetry you're using is also coming from satellite altimetry.
It's, well, we know how it's created. Okay, there are spot measurements, but then the satellite gravity is used to sort of give the higher frequency content. Okay, there's sort of spectral mixing. I mean, the point you're making is a very good one. As time progresses...
I think I should state the point I'm making, because isn't there a circularity?
Yeah, well, there is potentially a circularity, depends on where you're working. Okay, because if you're looking, for instance, in the North Atlantic or the Gulf of Mexico, or on certain rifted margins with a lot of oil and gas, we have very, very good bathymetry. And that, it's GEBCO who do most of the work. That data has been put into the mix where it uses the satellite, the satellite gravity as well. It's important to actually see where that data is. Okay. The other thing is that prior to inverting full MOHO in 3 dimensions, we apply a Butterworth filter to take out the short wavelengths, and that filter is set at 100 kilometers. Okay, but the point you make is a good one. But as we've been hearing this week, okay, there's a mission now to actually greatly improve real bathymetry globally, and that would be very much appreciated. The irony is that probably the best data set we have is the free air gravity itself. The other data that needs to be improved, or the better the data quality, the better the result, is the sediment thickness. Okay, that to me is the biggest problem.
And one other data set I'd make a call for is better marine magnetic data from, I mean, you have used but hardly mentioned marine magnetic lineations. All the reconstructions with G-plates depend on those, and that data set has been almost static for decades. Nobody really goes out and collects marine magnetic data to improve the lineation map anymore.
Okay, can I interrupt there? I think that sort of conversation could continue over tea, couldn't it? And for those who wish to join Rob and Nick in a detailed conversation on those issues, please find them in the lower library. If we reconvene back here between 2:45 and 5, that would be great. Thank you very much.
Thank you.
Okay, thanks.